happy day. Okay. Also paired with, in this webinar series, TriLogic, if you're in the Northeast section of the United States, they're going to be your TriLogic has working in the design for over 30 years and is able for solutions for graphics as well as for product lifecycle. If you're interested, you can reach out to TriLogic and we can discuss more on the in order to continue engineering data. TriLogic is been working with graphics and continue again, just like if you're down below with Logic, feel free to reach out in order to information on any tools or get an evaluation of any of the software you might be interested in. Okay, so here is kind of just a rundown of the territory that we can work with. So you'll see Oasis Sales is in the Northwest and central section of the country, while TriLogic is on the Northeast and East of the country. Okay, so we have quite a few webinars we do every month. So if you like what you see today and like what we've done before, please take a look at our YouTube channel. You can find them for Oasis Sales, or you can go to our website, .com, as trilogic.com. They also webinars every so often, and definitely check them out in order to get some of their webinars that have been really well. I'd like to just toss out if we go ahead and get started for the next webinar that I'll be hosting, and that's going to be on Thursday, August 30th. We're going to be talking about analyzation within the Expedition flow. So we can analyze our designs using a tool within Expedition and create the manufacturing output there. We're going to be focused on pads, professional, and Expedition. So if that sounds of interest, maybe jot that down there and hope to see you there. Okay, here's my contact information. Again, my name is Kyle Lake. I'm an application engineer with Oasis Sales. Feel free to reach out to me with any questions that we talked about today, or if you need any other, I'm always available. Just to make sure everybody's aware, you do have the ability to ask questions during this webinar, so there should be a little GoToMeeting pop up on your screen that allows you to go into the chat window and ask me questions directly. I have muted everyone just to negate any extra talking or any noise that anybody might have. So if you have any questions, please feel free to use that chat box and I'll answer those accordingly. Also, just I wanted to note out that this presentation is going to be recorded. It's going to be up on our YouTube channel, as well as we'll send out an email to that link within the next few days. Okay, so let's go ahead and hop in to talking about HyperLynx multi-board analysis. This is I like to always talk about the different offerings that we can help with within Mentor Graphics solution for printed circuit board design. So on the actual board design level, we have Expedition, which is an enterprise level tool. It offers really unlimited horsepower on the layout side, as well as great wraparounds for data management, collaboration through multi-site and multi-team efforts on your printed circuit board design. Pads is more of a project-based PCB design tool. It's been around for many years. It's still a very capable tool. You can output a lot of high complexity designs with it. It just doesn't include those data management wraparounds or enterprise needs that you might require. What we're going to be talking about today, HyperLynx. It's for PCB analysis and verification. So HyperLynx is a fairly large family of tools. It can simulate signal integrity, power integrity. We also have a graphical rule checker for EMI and other SI checks that can check for things that you would not normally notice in a standard DRC in your layout tool. And then on the PCB assembly, test, and manufacturing side, we have Valor. Valor NPI is an industry standard for both design for manufacturing checks and assembly checks. Okay, so if these sound interesting, again, feel free to reach out to either TriLogic or Oasis Sales for more information on any of these tools. So why do we need to consider doing multi-board analysis on some of our designs? So this graph on the right-hand side essentially is showing that that red line is the average leads per square inch. So our designs are getting more and more packed with more and more functionality, smaller components, more interconnections, and we're still attempting to do that in the same time, in the same design spin that we have always been doing that. So what does this mean? We can always have multi-board systems. There are many people, I'm sure, today are doing multi-board systems in their designs. So it's very important to be able to simulate the propagation of signals from the motherboard to the daughter board in order to ensure that that signal integrity is staying high throughout that interconnection, as well as any connectors that are connecting those two boards. Okay. And that design on the top left, that's actually a design winner for Mentor Graphics. They hold a design contest every year, and that's just was actually done with pads layout, and I'm sure there was simulation done on that board as well. Okay, so multi-board analysis. How do we use HyperLynx in order to enable multi-board analysis? So it is actually very simple to go ahead and use the MultiBoard project wizard to join different board files into a single analysis database. I'll walk through this to show how we can point to one design file and point to the other, and essentially make them through defining the connections that we have across those different boards. Okay. What we can do once those are actually mated in the multi-board project now is simulate that signal integrity and the crosstalk issues at the board boundaries as well as through the board connections. Okay. What kind of board files can we read in? We can read in HYP files, ODB++, and CCE files. So HYP has been around. It's been a HyperLynx format for quite a few years. ODB++ is definitely gaining traction as a manufacturing output, and then CCE is the Mentor Graphics format from Expedition or pads directly into HyperLynx. So again, very simple to get the correct design items or the correct board formats in order to create a multi-board project. And some of the analysis features that we have within the HyperLynx tool is batch SI and crosstalk analysis, interactive analysis with the oscilloscope. We can take nets that we might be concerned about in the board sim space and export them into a whiteboard environment called line sim that essentially allows us to do what-if analysis on stackup parameters, connections, and which layers those traces have been routed on even. We can go down that far. As well as we can current probe throughout the design using the multi-board analysis. Okay. And once again, I'm not seeing any questions in the chat yet, so please let me know if you all right, I'm seeing a few questions, and I'll get to a couple of those just in a second. So here is creating a multi-board project. Again, what we have to do here is just point to the HYP file, ODB++, and CCE. And then the actual multi-board project wizard, as we can see on the left, the top left picture there, is it's showing the actual files, which reference designators we are connecting to which reference designators on the motherboard and the daughter board. All right, so once we have both of those design objects, we have to join the boards by declaring the connectors that we have throughout the board. So you'll see we have a connection editor that allows us to point which connections or which pins on connector J2 and connector J1 are connected together. Okay, and if we would like, we can actually go ahead and assign a connector model to those connectors for more advanced analysis. So Mike Earp, I see that your question is, can a cable connection between boards be analyzed in aggregate analysis? Yes, definitely. So we can insert an S parameter model or a SPICE model for use as our connector, and then actually use that in our simulation in order to provide the highest quality and closest to real world result simulation that we can. Okay, so how are stackups handled within the multi-board analysis? This can be a little bit tricky of how to set this up. And within the stackup, essentially there are two stackups that are hosted in a multi-board project, or 3 if you have 3 different boards. So essentially, you can have a pull down that shows this is the stack up for the main board, and then this is the stack up for the daughter board as well. So all of that stack up information is brought over via the ODB++ model or the HYP model. Okay, so very easy to bring in all that information. You don't have to go ahead and set that up by hand. You can, in that stack up editor in the top left, we can do some what if analysis in there, play around with the different dielectric constants that you might be working with, or thicknesses that you might need to adjust. And you can work with your manufacturer in order to get those values as close to possible as what they're using. So also for the connector models, we can have 3 different types of connector models. Essentially, we can short the 2 boards together for essentially some ideal simulation. We can also do a simple RLC type model of those connectors, or we can actually use an advanced model of, using an S parameter or SPICE model in that connection. Okay. All right, so what we can do on the analysis realm, once we have this multi-board project set up, is we can actually start doing some signal integrity analysis. Okay, so the first thing that we will need to talk about is how do we set up and assign models to the actual components. Okay, so the easiest and most effective way to model our different components in the HyperLynx realm is to use IBIS models. Those are very usually free and readily available to get from the manufacturer, and it's very easy to go ahead and assign those to our different components. We can use 2 different methodologies to assign those IBIS models to those components. We can use reference designators or part numbers, or we can just go on a one-off basis and actually go ahead and assign them one at a time. So what we can do within the simulation realm is we can actually start off with running a batch SI and crosstalk check. So what the batch analysis allows us to do is essentially check as many nets as we want on the entire design. You could check all of them, you could check just a few buses, or just your critical nets. And it's going to go ahead and run the batch simulation and highlight any signal integrity issues that we might have, length violations, crosstalk violations. Anything that we set up in that batch SI check is going to be flagged, output an HTML report for us, and allows us to share and collaborate that with our different users. So the batch check is a really good way to start off with your design. It allows us to highlight any areas that you might have some major signal integrity issues, and then we can delve down and actually go ahead and run SI checks on single nets or buses one at a time. We can do rising edge, falling edge type simulation, or oscillation in order to understand how that interconnect is affecting your signal integrity. We also have the ability to place quick terminations at either die in order to hopefully negate any reflection or impedance mismatch throughout your transmission line and see how that affects through there. So that's kind of what we do in the layout realm. And then if we understand that we have a net that there's some serious signal integrity issues running from motherboard to daughter board, we can export that entire net from the post layout tool in order into the whiteboard analysis shown right below the oscilloscope there. That's actually showing what that interconnect looks like using transmission line models, via models, and then driver and receiver. So within that environment, we're able to do a lot more playing around and adjust parameters in order to see how to fix any signal integrity issues that you might be seeing. All right, so I didn't want to bore you to death with slides. So that's kind of what we're going to be showing off today in the HyperLynx tool. So I'm going to go ahead and hop right into there right now. Okay, so this is the HyperLynx tool. Again, if anyone's not aware of what the HyperLynx tool looks like, it's pretty simple, easy to use environment. And what we're going to do today is we have the ability to go ahead and create a new SI schematic. That's for the pre-layout analysis to do help develop our design constraints, a new board where we can actually import a board file and then do the post layout analysis. But today we're going to be talking about the new multi-board project. So all I have to do here is click on this for a new multi-board project, and I'm going to just go ahead and name this Kyle's multi-board. So I can browse and place this wherever I'd like. So now what we have to do is we have to actually insert the different boards that we're going to be working with here. Okay, so all I have to do is click on Insert and point to the different HYP files. For this case, I'm actually using the HYP file format, but like I said, we have the ability for HYP, CCE, TGZ, and then XML for the IPC 2581. I did see a question about that, and yes, we do support that too. Okay, so I've got the main board in there. What I can do is I can actually enter a comment if that would be helpful for you to enter that in to just make sure you understand which board is which when we're actually working with this project. Okay, so I'm going to use the plugin board as well, and I'm going to name this plugin 1. So what we can do is if I have this main board with 2 of those plugin instances, I can use that plugin1.hyp as 2 different boards. Okay? So I can have a plugin 1 and a plugin 2. All right, so next what we have to do is we actually have to define what is connected to what throughout these different boards. Okay, so I've got my design file 1. I'm going to select that main board, and our first connection is going to be from J1 on the main board to J1 on the plugin 1 board. Okay. Next, I'm going to select J2 for the main board to the plugin board to J1. Okay. All right, so once I have both of those inserted, you'll see on the left-hand side, I've got J1 for the main board connecting to J1 on the plugin 1, and J2 from the main board being connected to J1 on the plugin 2 board. Okay, so that's all I have to do. Very simple, very easy. Next, we have to actually define what these connectors look like. So we have 3 different ways that we can model a connector in this multi-board project. First, if I want, I can do a short, essentially shorting these 2 boards together. Ideal simulation, we're just going to see how the signal propagates from the main board to that plugin board. If I'd like, I can actually just do a simple RLC model. And again, this can be easy if we don't want to have to go out and get the connector model, we can really quickly use this. And I can adjust the inductance as well as the capacitance, and you'll see that the impedance and delay are automatically calculated for us. Okay, so if I have an inductance of 10 nanohenries and 1 picofarad, we're going to get an impedance of 100 ohms and a 0.1 nanosecond delay. So just to start off, I'm going to go ahead and work with the simple model on both of these connections. And like with all Mentor graphics tools, if I click on the help icon here in any of these dialog boxes, what that's going to open up is it's going to actually open up an HTML documentation page that really explains exactly what every option does in this tool or in that particular dialog box. All right, so once I click finish, it's going to go ahead and make these 2 boards, and hopefully we will see our new multi-board project. Okay, so up at the top, you can see we have our different reference designators, all suffixed by _BOO. Okay, so R15_BOO. That is the suffix for our main board. And if I go down a little bit, you'll actually see that these other boards have _BO1 and _BO2, just to make it simple for us to understand which reference designator is on which board. Okay. So if I zoom in just a little bit, we can actually see the connections between the different boards being signified as these dashed lines. So these dashed lines are running from a net on this plugin board 1 through this connector up onto this other board or the main board. If I'd like, I can actually just right-click on a net and select that net, and that will highlight throughout all of those boards that are connected electrically for that connection. Okay, I'm going to go ahead and open up the stackup editor, and we will see that the stackup is being brought in correctly. I did see a question on, for some reason, the HYP file not bringing in the stackup, and that may be due to an older format of HYP or just some sort of issue. We might have to take a look at that a little bit closer. But what the stackup editor allows us to do is it allows us first to visualize what that stackup looks like. So it gives us an actual cross-section of what that stackup looks like. Also associated are all the different layer colors and the substrates in between those different layers. So this tool, like I said, we've got this drop-down menu for the board definition. So right now I'm looking at the stackup for the main board, and the tool realizes that the plugin 1 and plugin 2 boards share the exact same stackup. So if I select on that, we'll see that the stackup changes. If you'd like, we do have the ability to do impedance planning within the stackup editor. If I'm shooting for a target impedance of 75 ohms, it will calculate the correct width for us of a single-ended trace. So if I need to change that target impedance, hopefully that width will change, and it does. We also have the ability to solve for differential pair impedance, and I can solve for the separation of that differential impedance, or I can solve for the width of both of those differential pairs. Okay. All right, so what we've done so far is we've gone ahead and created our multi-board project, and then we've ensured that our stackup has been brought over correctly. The next thing that I like to take a look at is just ensure that our IC models have been defined. Okay, so within HyperLynx, we have the ability to assign models by reference designator, and that's what I've gone ahead and done for this particular project. You'll see down here at the bottom, I've got a reference designator model assignment, and any component that has this reference designator is going to be using this IBIS model that we have defined here. So if you need to, you can actually go ahead and select these different components and actually assign models to them if you need. So this is, if I need to assign a model to this mounting hole for whatever reason, I can go ahead and assign an IBIS model to that. Okay, so very easy to assign models on the fly as well. If you'd like to, you can build also a QPL file, it's been called. And what a QPL file does is this will be your HyperLynx IBIS model assignment tool. And what you can do is actually take part names that you're using and assign an IBIS model to them. How this can be useful is if you set this QPL file up once, every time you use that part in a future HyperLynx analysis, it will automatically pull that IBIS model and use it in a simulation. Okay, so we have our board set up correctly. Now let's go ahead and hop into some sort of simulation. So if I do the Simulate SI pull down, you'll see we can go ahead and run an interactive simulation on a single net if we would like, or run an interactive sweep of certain net. But what I'm going to do here first is I'm going to run a general batch wizard. What I can do is, I'm just going to go ahead and click on that. And I'm going to actually import a setup file that I've gone ahead and created. So what we can do within here is we can run both signal integrity checks as well as crosstalk checks. Okay. Angelica, I see that your you're saying, if I build a PCB with SPICE VHDL models, do I need to change all my models to IBIS? We do have the ability to simulate with SPICE. VHDL within HyperLynx isn't going to be supported. You might need to look into getting some IBIS models for those components. All right, so stepping through the general batch wizard, what we can do first is I can actually select the different nets that I want to actually simulate. So I can either simulate all of the nets on the board, which it can definitely be useful, or it can take some extra time in the simulation. But if I know that I only want to simulate a certain bus, for example, I can just select all of these nets, the A nets. Okay, so you'll see again, we've got AO underscore B00, AO underscore B01, meaning the plug-in board number 1, and then A0B02 is the net that's plugging in to that second plug-in board. Okay, so it's again finding that those nets are propagating through all of those different boards and allowing us to analyze them through there. Okay, so what we can do here is we can actually go ahead and set up our different simulation settings. We've got crosstalk simulation, signal integrity problems caused by line lengths. So what this is going to be utilizing is our terminator wizard and actually kind of understand if these nets are going to be too long and cause some sort of ringing or other signal integrity issues. So within the terminator wizard, we can actually utilize IC input capacitance and trace impedance. So this tool is going to be running HyperLynx signal integrity checks just using the general batch wizard in order to quickly identify any large issues that we might have in our board. So it will go ahead and get all of our interconnect statistics and output this in our HTML report, allowing us to parse that data a little bit easier. So here's our actual simulation settings. We have the ability to use our different IC model corners. For this simulation, I'm just going to go ahead and use a typical simulation setting. Okay. We do also have a section for default IC model. So if you don't want to go ahead and select an IBIS model for each individual IC that you have on your board, we can use this default IC model in order allowing us to go ahead and simulate a little bit quicker without setting up an IC model. This might not be great if you're looking for some very, very accurate simulation, so it might be more advisable to go ahead and assign IBIS models to every single component that you have on the board. All right, just some more crosstalk settings. It's going to do a crosstalk iterations of an auto amount just to feel how comfortable it is. And then we are going to say that we have all of the aggressor nets are active. And then in our reporting options, we have the ability to create a summary report, HTML report, and then Excel as well. Okay. So once you have this set up, we can save this setup file in order to use it very quickly in the future without having to reset up all these simulation settings. Okay. So I'm just going to go ahead and click run. It's just going to take a few seconds in order to simulate all of our different nets that we are. Okay, so here is our HTML report that has been generated from. So in this general summary tab is essentially giving us if this net has failed or passed our different checks. So if we have a violation in the termination, the quick analysis crosstalk, or the detailed and crosstalk, I can actually click on these hyperlinks and it'll take us directly to that section, giving us a little bit more information on what's either passing or failing for that particular net. Okay. So there's a lot of information going on in here, but if I take a look at our termination, it will actually give us our different violations that we're having. So it shows us that this 4 net, that it is far too long using the setup things and the IBIS model had assigned for it. It said its found length is 5.4 inches. And it thinks that it only needs a 1-inch trace and fix that. So it can be something that we can take a look a little bit further and then do some more simulation on. If I'd like, I can actually go ahead and select this net in the HTML report, and it's going to go ahead and select that back in the HyperLynx tool. Okay, so that's pretty nice that this HTML report allows us to do cross-probing between the HTML and the actual HyperLynx tool. Okay. So there is the general info, just gives us general information about the stackup. So in this HTML report can be full. You run your first initial simulation, you use it as a design review tool that allows you to see all the stackup information, whether we're passing or failing, our cross, or other SI checks that we're running. In the quick analysis and crosstalk, we're seeing that we're getting quite a bit of crosstalk on these different nets, and our max allowed crosstalk in electrical threshold was only 50. So that's a pretty small for crosstalk. So what we can do here to alleviate this issue is maybe think about allowing us to have maybe bolts of crosstalk. We can actually play with up to adjust that, maybe look at how the traces are routed, understand why we're getting so much crosstalk, especially on this A14 net. All right, so once I've gone ahead and ran our SI check, now what we can do is actually delve down a little bit further and look at maybe one net at a time and understand how that's going to work. So if I want to take a look at this A15 net a little bit closely, first I'm going to look at the models that we're using. Okay, so I'm going to click on the Assign Models dialog, and you'll see first I'm looking at U14.11. So that's on the plugin board 1, and it'll actually show us which model we're using, and then that is the actual output for that model. Okay, so this, if I click on all these models, it shows us the different models that we're using for those components on those different boards. Now, with that selected, I have the ability to actually run simulation on it. I'm just going to click on the Run Interactive Simulation and bring up our digital oscilloscope. So the digital oscilloscope essentially works just like an oscilloscope that you would have on your lab, and actually the different probes that we're using are our different arrows in the workspace that we see here. So we have, it looks like, 7 probes working on this design right now, and they're all color-coded. So within the digital oscilloscope, you'll see all of our different pins have a color associated with them at the far right-hand side. Okay, so that's just the different colored probes that we're going to be using. Within the digital oscilloscope, I have the ability to run an edge simulation. Right now, it's just a rising edge, or we can actually do an oscillation and define the frequency and duty cycle that it will be running at. Okay, so I'm just going to run a rising edge on this board, on this net. And again, looking at the different models that we want to look at. So right now we're going to be looking at plugin board 1 running into the motherboard, essentially to U100 is going to be the receiver. Okay, so it looks like there is some overshoot going on from the driver to that receiver. Okay, so there's a lot of different things you can work on in order to hopefully alleviate this issue. So this helps us identify a little bit more of an issue. Now what we can try and do to solve it is actually go ahead and use some of the tools within HyperLynx. One thing that we can do is add a quick terminator. This allows us to assign a termination model at the die of either the driver or the receiver. Okay, so you'll see here that I can actually add a series resistor on the die of U4. So that will be right here at this kind of blue arrow, and I can actually adjust this value if I would like in order to better fix that issue. So I'm going to change that to 100 ohms, and hopefully we will see how that changes. Within here, I can actually adjust what layer this series resistor and what length and width this trace is being ran at as well. Okay, so this allows us to play around in order to fix some of those issues. So once I've changed that value, what I can do now is I can again run that simulation, and hopefully we will see that it's got a little bit better. So I have the ability to turn off the previous waveforms, and we'll see that it has actually adjusted that overshoot quite a bit, just changing that series termination value from 50 ohms to 100 ohms. Okay. If you would like to actually delve down into this a little bit deeper and understand how we can fix this without adding an actual series termination resistor, we can actually export this net to the freeform schematic. Okay, so what that's going to allow us to do is it's going to take all of this interconnection info that we see in the board sim tool here and allow us to have it in the line sim tool, which allows us to do a lot of what if analysis. Okay. So as you can see, it actually pulls in a lot of different information from this interconnect. These cylinders, the transmission line icon, those are the actual transmission lines of our signal propagating from that plug-in board to the motherboard. So you'll see this via, it's showing that we have a connection from the top layer of BO1 being plug-in board 1 to the inner layer 4 of that exact same board. Okay, so this tool gives us a lot of different parameters based on those different T-line aspects. So if I double click on this transmission line, it'll actually bring in the information that we see. You can go ahead and I can change this from the stackup values. So you'll see that stackup is automatically calculating the characteristic impedance, the delay in seconds, and the actual resistance that it's seeing. Okay. If you'd like, within this tool, I have all the ability to go ahead and change it to a simple model. I can actually edit or input these values myself, or I can change it to a microstrip and adjust all of these values as you see fit. Okay. If you would like, you can change which layer that signal has been routed on in order to see how we can fix that and see how that affects the signal integrity that we're seeing. Okay. So right here, we will see that it's still on the plug-in board 1, and you'll see that this resistance here is that 1 milliohm resistance that we have set for our connection right there. So if I double click on that, you can see that it's that R0003 for that connection value. So this is what's signifying that we're transitioning from plug-in board 1 to the motherboard that we're actually seeing there. So within this tool, you have the ability to do a lot of what-if analysis, adjust all of these different properties. You can adjust the via type that's used, the transmission line, how it's affected by the stackup. And then once you're ready, I can actually go ahead and re-invoke the simulator and the digital oscilloscope. Okay, so that signal looks pretty good, and that may be due because there is our series termination resistor that we have set up from that quick terminator. If I want to, I can go ahead and quickly delete that, reconnect those there, and then do a resimulation. Okay, so it looks vastly different than what we had in the previous waveform. So that series termination resistor that we were working with was definitely affecting the signal. Okay, also within here, we have the ability to run sweeps. So if I want to do an interactive sweep simulation, I can set this up. And there's a lot of different things that we can sweep within here. So we can sweep the stack up itself, the different layers. If I want to go ahead and adjust this inner layer thickness, I can add a range and it will sweep those simulations for all of those different ranges. I can sweep power supplies, IC modeling, the coupling regions themselves, and then also the transmission line. Okay? If I want very easily, I can go ahead and sweep the connector. So this resistance is for the connector between plug-in board 1 and the motherboard itself. And I can add a range very easily. So if I want to change this resistance for that connector from 1 milliohm and sweep it all the way up to 1,000 milliohms or 1 ohm, I can actually go ahead and set that there. I can set the simulation count, and it will automatically create all of those ohms, or the different lists that we have for that simulation count. Now I can run the sweep, and I'll go ahead. I see a question asking, are all the tools you're showing included in the HyperLynx SI tool, or are there more modules? So the multi-board analysis is included in the HyperLynx EDR tool. So there's not really an extra module that you have to purchase as well. Okay, so those sweeps didn't make too much of a change, but you'll see as I actually go over with my cursor, it'll give us those different waveforms and show us what those different values are. So you can see that I'm looking at the 1 ohm right there on this line, and I can actually look at all those different sweeps that we ran. All right, so the last thing I'm going to talk about is how we would actually go about using more of an advanced model for this connectors. So again, when we set this up, the connectors that we used were those simple RLC models. If I go to Edit Multi-Board Project, this again will bring open that project wizard that we started working with. And I can actually go again to our connection definition. So if I want to, I can click on the advanced connector model, and I can just assign an S parameter model. So that will be that S4P model that we're looking at. Okay? So I just have a few example files in here. These are just 4-port S parameter models, and you can hopefully get these from like the actual manufacturer of your connectors, or we can create those within HyperLynx using 3D areas and solving Maxwell's equations. Okay. So I'm going to just go ahead and use the example S parameter model that we have defined here. So you'll see now I've changed this from a simple model to an advanced model with that S parameter that we're using. Now if I click on the connection editor, this will show what that connection kind of looks like with this S parameter defined in between. If I double click on these different ports, it's going to push them over to the right side, and I can actually go ahead and start defining which pins are connected through this S parameter. So if you have an actual connector model, it will probably be a much larger port model, I'm sure, but if you want, I can just drag and drop these different signals onto this port. In order to define that connection. Okay. When I hit finish, now we'll see that instead of those 2 large RLC connectors, we have a much smaller connector that has been defined through that S parameter. So then once you have the S parameter set up as your connector model, again, we can go ahead and just run a general batch wizard or interactive sweeps or the simulation, and it'll be now using that more accurate model for your connector. All right. So that's all I had to show today. Again, thank you everyone for attending. I don't see any other questions in the dialog box. I did see some questions that I'll be answering privately, just because I didn't think they would be good to answer during this presentation. But again, here's a save the date for our next session. Again, it's going to be with panelization in the expedition flow. That's going to be on Thursday, August 30th, same time, It would be useful for PADS professional users as well as Expedition users. I'll be talking about how to use FabLink in order to generate manufacturing output. All right, again, here's my contact information. Feel free to maybe take a screenshot of that or write that down. Always happy to answer more questions or talk with more solutions with you. Okay. All right, thanks again for attending. I hope everyone has a good rest of your day.